Okay, so thank you very much. Well, first I'm going to start sharing my screen just to make sure that this is working. So hopefully if I do all of this, you'll be able to see
Yep, yep,
my screen.
yep.
And if I do this, you should see the laser pointer.
Yeah, we do.
Okay, fantastic. All right. Well, thank you very much for the invitation, the opportunity to talk to this. I think it's a great initiative. I think it's really fantastic to be able to organize all those talk online. I know that my students are enjoying them in this and for the opportunity to talk here. So as you can see, I slightly changed my title. I thought rather than talking for a whole hour, we'll make it just half an hour, and I'll be focusing on some specific materials rather than a whole range of different materials for bioapplication. So I'm going to talk about the specific system that we've developed, cyclic peptide polymer conjugates. So I'm going to go straight into it. These are systems that we've been working on for quite some time. They're basically based on cyclic peptides, which are synthetic peptides. They are based on alternating amino acids, L and D amino acids. Typically, they work on 8 amino acids that are then just linked into a cyclic peptide. These were developed by Gadiri and Granja in the mid-90s. And the secret of their structure is on this alternating L and D amino acids. So what it means is that you'll end up having the carbonyl group pointing either up or down on the cycle. And having this conformation allow the cyclic peptide to stack on the top of each other. And as you can see on this example, they're going to start just forming hydrogen bond and eventually form tubular structures. Now, those tubes don't tend to be very stable and they tend to be not very soluble. So our contribution to the work was to attach polymeric chain to the cyclic peptide before assembling them to the nanotube. So you got an example here of polymers. So for instance, two polymers attached to one cyclic peptide, and then we're just going to have stacking of the peptide and forming the nanotubes. We're not the only ones to have thought about this. Bizalski and Berner independently came very similar idea around the same time. And to grow the polymer away from the peptide. You see that we use this as well, but we tend to prefer making the polymer separately and then linking it to the peptide after. So we quite like those systems. The polymer is really useful to stabilize the tube, but it's only recently that we started realizing that the polymer can have some other properties. So what you got here is some work that was done in collaboration with my colleagues at Monash, David Chalmer, William Parson. You can just about see his name here. Will is here. Came to Warwick to spend some time with us. And what David and Will are interested in is modeling of molecular structures. And our idea to do a computer model of the cyclic peptide stacking and of the nanotube. And basically what we found, if I can get the movie going, was that rather than having the chains of the poly chain actually tend to wrap around the cyclic peptide tube here. And those polymeric chains are going to really help for the assembly to be much, much stronger. So it's not just providing steric stabilization to the tube. It's also allowing to, if you like, wrap around the cyclic peptides and then just rigidifying the overall supramolecular structure. What Will was also able to do was to look into the specific energy required model here, which is an 8 peptide nanotube. And we started counting the number of hydrogen bonds between each of those cyclic peptides. So as you can see here, we're going to have the two ends. We'll have basically 8 hydrogen bonds formed with the rest of the structure. And then when you go into a peptide that is in the middle of the tubular structure, then we have 16 bond forms in there. So altogether, if we have 8 amino acids, 8 peptides, we expect 56 hydrogen bond being formed. 16 will be for both ends. So the 16 that are here, and then the other 40 will be for the core of the peptide. And basically what this at is looking into the hydrogen bond forming ending in time. And what we find is that there's a lot more breaking of hydrogen bond on the extremity of the tubes than there are in the middle of the tube. You can see here far less breaking. And what that's telling us is that the tubular structure, when it's breaking down, because it is a supramolecular peptides are breaking away from each other, it will be preferentially from the end of the tube rather than from the middle. So the tubes don't break in two or three or four as they fall apart. They actually shave off their end groups one after the other. And this is quite critical for the application in drug delivery that we're going to discuss. Now, sometimes we don't really want those to break away that easily, so we want to rigidify those. And the approach to this was Julia's PhD. So Julia is now an assistant professor at UCL in the UK. And basically, Julia's approach was quite simple, but I think very smart for her to think about it that way. She designed a system with a hydrophobic polymer, then attached to a hydrophilic polymer. So we made a block of polymer. So we use raft a lot. So we made a block of polymer using raft. We attach it through carboxylic acid to the lysine of the peptide. And the block of polymer is defined with a hydrophobic inner segment and a hydrophilic outer segment. So the inner segment will provide this hydrophobic inner shell or hydrophobic core around the cyclic peptide. And then the hydrophilic segment is going to provide with the stabilization in solution. And the reason why this is working quite well is because having this hydrophobic core around the peptide will prevent water to diffuse inside the nanotube itself, and therefore will prevent the water to disrupt the hydrogen bond. And by preventing this, we stabilize the overall structure. So we'll end up with structures that are much longer, but also much more stable. And I'll demonstrate this to you by using this technique called A4, so asymmetric field flow fractionation. So if you can think of this as similar to a GPC, so it's a sort of an exclusion, a size exclusion system, but the exclusion is not done via a column. It basically is done by diffusion of your molecules. So we have a flow of your solvent with your molecule going in one direction, orthogonal to the initial flow. And basically what will happen is that the bigger particle will tend to move out slower than the small particle. So you're going to be able to separate slowly your small particle from your big particle. Now of the A4, we have a detector, so for instance, a light scattering detector or a concentration detector, such as a differential refractive index detector. And that will allow us to separate structures. So we will separate the peptide polymer conjugate from the nanotube structure. And I should have said that if we were to just break the supramolecular interaction, so it's very difficult to see the actual tube with this system. So here is a first example, and as you can see, we're using dimethylacrylamide as our graft, as a polymeric chain attached to the cyclic peptide. And we're also using a raft-made polydimethylacrylamide as a control. So we've got here a DP50, and that's just a linear chain, and we see that this is going to come after about 10 minutes elution time, or exactly 9.5 minutes. Now, if we attach the polymer to the peptide, the all conjugate, so the actual conjugate, not assemble, will come out about 10.7 minutes. And the actual nanotube comes much, much later, and this is what you can see here in the black trace. So in about like 15 minutes, we can see the conjugate, the assembled conjugate. So basically, A4 is really powerful to differentiate between the nanotubes, so the assembled conjugate, versus the free conjugate in solution. And as you can assembly, we have quite a lot of conjugates that are not assembled in nanotubes and exist as what we call unimers. So just the peptide with the two polymeric chain attached. And then you can see here the nanotubes. Now, if we do Julia's trick of introducing a hydrophobic block in the middle core, so we're now looking at this structure here. So this is not a graft. So the butyl acrylate block is attached around the cyclic peptide. What we find is that in this case, so we're looking at the black trace, now we have almost exclusively nanotube. And in fact, it looks like we have some larger structures And we think that these are actually still nanotubes, but longer nanotubes. And it seems that they tend to assemble in a discrete type way. And we can compare this to our control. And in green, what we've done is a control with the block copolymer alone. So in this case, there is no peptide. So we're forming an amphiphilic block copolymer, which we expect will assemble into particles, so probably micelles. And you can indeed see the micelles here, 14.1 minutes. And here is the unimer, so the block copolymer that is in solution. So if I look into this graph here, I'm comparing directly the system that we call dynamic, so with the 100% hydrophilic polymer graft, and the diblock copolymer, where we're having this what we call the stabilized structure. See the difference. So here we have the dynamic that is showing us the unimers and the assembly. As you can see, we have exclusively nanotubes. So there we have nanoparticles that we can use for our application. So our application is in drug delivery, and the first thing we need to assess is their toxicity, but also their biodistribution, because we're going to use these to be able to carry drugs around the body and just try to deliver specific drugs. So that was work that was done in two PhDs following each other. So first Andy and then Sean. Andy's PhD was about molecular brushes, so covalent molecular brushes. And I've got here a cartoon trying to show you how both structures are very close to each other. So we got here the nanotubes that I've presented to you. And on this side, we have polymeric brushes made by Raft. So we got a covalent backbone and acrylamide covalent backbone. And then we have graft. And in this case, we're using an acrylomorpholine, which is a polymer that we like very much for bio applications. And then here we have effectively the equivalent, the supramolecular equivalent, where the backbone is now made or built through hydrogen bond between the cyclic peptide, and the graft has still this NAM made polymer. And the idea is that to inject this structure, so as you can see, the dimensions are very similar. So we got tubes or structure about 40, 50 nanometers long and about 4 to 6 nanometers wide. And then we inject them into an animal, and we look into the time it takes for the structure to come out. And as you can see, for the covalent particles, we have a very long circulation time. And this is an issue. This is a non-issue for nanoparticles. We have accumulation. Those things tend to not come out. In fact, if you measure the amount of material that you collect, for instance, through urine of the animal, you'll see that independently of the size, so even for small structures as well as for big structures, we're collecting about 0.6 or 0.7%. So this is a percentage, 0.6 or 0.7% of the material after 24 hours. So this is a problem because we have effectively accumulation, and that could lead to toxicity. If we look into just the graft and we inject the graft, what we'll find is that the graft gets excreted very, very quickly. So you can see that after just about 500 minutes, the system already, our linear NAM is going to come out. And you can see we just collect about 51% after 24 hours. So in this case, it's the other extreme. It goes out too fast, and we don't have time to use this. It's not long enough to circulate. It's going to be very difficult to target specific organs or cells with this system. Our supramolecular polymer is just in the middle, as we would have hoped. So because of the supramolecular structure, we have a nano object, so it's quite large, so it will be distributed throughout the animal. But eventually, the conjugates are going to fall apart, so they're going to shave off the end group bits by bits, and slowly they're going to be excreted. And you can see in the specific time, what we're looking at is about 30% of our nanotube is excreted within 24 hours. Now, this is the dynamic system. So that's a system where the graft is 100% hydrophilic. If we look into the more stabilized system where we have this diblock copolymer, where now we're introducing a hydrophobic inner shell, and as you remember, this will help to stabilize the overall structure. As expected, we have a slightly longer distribution time. In fact, if you look into 48 or beyond 72 hours, you'll find that these are actually circulating very long time. They're still supramolecular, so they're still going to fall apart eventually, but that really enhances their biodistribution. So in other words, we have a system that is looking very promising for drug delivery. So let's have a look at its drug delivery activity. So that was the PhD of Sophie. Sophie here, who is now a postdoc in Cardiff University in the UK. And Sophie approached this from two different angles. This is the generation one of her systems, where effectively she uses cyclic peptides. So you'll find we use the same structure quite often. She functionalized it with a drug, an anti-cancer drug, and in this case we're using camptothecin. And the other side is a polymer that is going to be there for the stabilization of the overall structure. We assemble those structures in tubes, and we're comparing the dynamic structure with the hydrophilic chain, and then the more stabilized structure where we have our inner shell, hydrophobic inner shell. And basically, we're going to compare those two structures together. So the first thing to look at is the hydrolysis and how fast we can hydrolyze the drug. And we have another iteration of the system where we're looking into the linker. So hopefully you can see on your screen, we've got here a linker that can be hydrolyzed, and we've got here another linker that can be hydrolyzed but much more efficiently. So this linker will be hydrolyzed faster. And then we're comparing, so if I start from the top, the dynamic system. So if you remember, water can penetrate straight into the cyclic peptide core and therefore attack the ester bond where the drug is attached. And then we have quite fast hydrolysis. And depending on the liquor, we can have very fast hydrolysis or slightly slower. But then when we use the system with the inner shell, the hydrophobic inner shell, water penetrates slightly, the penetration of water is slightly slower. Therefore, we have slightly slower hydrolysis if we compare the same linker together. And again, we have even more fine-tuning by changing the linker. So we really have this whole range of rate of hydrolysis of our drug, which is fantastic because it means that we can deliver the drug at different speed. So this is just the theory. Now, if we look into the practice, so we're looking into 2D cell culture here, and what we're effectively looking at is the IC50, so the concentration required to basically kill 50% of the cells. So these are cancer drugs. So we're looking at killing the cells. So we're looking into a prostate cancer cell line. And what we find is that, so camptothecin is obviously very effective, so very, very efficient. And then we can differentiate our system and also correlate very nicely with the rate of hydrolysis. So you can see that the more stabilized system with the slower hydrolytical linker will require higher concentration than the one with faster hydrolysis. And the dynamic system will always be faster than the stable system. So this rate of hydrolysis translates into effectively activity. And you can see here our control, which is basically making sure that both nanotube system without the drug are non-toxic. So the toxicity really, or the activity really comes from the drug. So this is 2D cells. We can also look into 3D cells. So we're using spheroids. So spheroids are basically a culture, a very complex culture of cancer cell, and we're trying to mimic a solid tumor in this case. By treating this with a compound, what you expect is that if you have no treatment, so if we look into here, for instance, if you have no treatment, you're going to see that your spheroid is going to start growing. So you're going from day zero, to day 4 to day 8, and you see that the cells are multiplying and your spheroid, so your artificial tumor is growing. If you treat it with our system, what we find is that we're really just preventing the growth. And this is exactly what you want the system to do. So effectively, our system is really just going to prevent the growth of the spheroid, and therefore not just killing the cells, but preventing the overall growth. So that works fantastic, and we're very excited about this. There's only one issue before going in vivo with this system, and that comes down to the design. So if I follow slides back, we have one drug per peptide, which means that the drug loading is very limiting. So we only have one drug per peptide, which means that the whole loading will depend on how many peptides we have to assemble in the nanotube, and we're correlating the number of drugs to the size of the nanotubes, and that's not ideal. So Sophie designed generation 2 materials. And the idea here is that instead of attaching the drug to the peptide, we attach the drug to a polymeric structure attached to the peptide. And by doing this, what it means that we can now polymerize many drugs and have however many drugs we want attached to the peptide. So we can have 1, 2, 3, 4, and that allows us to fine-tune the drug loading. The other aspect here is through the chemistry. So I won't insist too much on the chemistry here, but you can see that we're basically growing a polymer away from the peptide. But we're attaching the drug through an ester bond here. And the idea is that the drug in this case is SN38. It's a really hydrophobic drug. So we're doing two things with one reaction. We're creating this hydrophobic inner shell, thanks to SN38 being hydrophobic, and we're also functionalizing with the drug. And what it means is that as the hydrolysis will occur, we're going to start delivering SN38, but we're going to lose the hydrophobicity of this inner shell, and therefore our system is going to be more responsive and fall apart faster. And of course, as this is getting more hydrophilic, then we get more hydrolysis. So it's kind of a nice built-in system where we're engineering together both drug delivery and disassembly of our structure. So you got here some examples of the characterization, of the structure characterization. So you can see here some nanotubes, for instance, by TM, and we use a lot of scattering, especially neutron scattering, to look into the behavior of a system in solution. So does it work? Well, we think it works quite well, actually. So we look into first the analysis of the drug. So we're comparing PBS as a control with mouse serum, and we found that we do have hydrolysis of the drug. So we are releasing the drug. So the concept is working. I think here, this graph is the most important. What we're looking at is the toxicity of the drug, or the cell viability. So the drug is here, and of course you want it to be very active. So you can see that we have quite high toxicity on our cells. So that's great. That's exactly what we want. We're comparing this to irinotecan. Irinotecan is the prodrug of SN38. So because SN38 is hydrophobic, it has to be modified into a hydrophilic compound so that you can actually use it in clinic. And as you can see, this makes irinotecan far less active, and you need to go to quite high concentration before you start seeing some activity on cells. Our polymer, our nanotubes are almost as efficient as SN38. SN38 to our nanotube doesn't change much of its activity unless irinotecan makes it much more efficient than irinotecan. And what you have here in black is basically what you have here in black is basically the fact that our nanotubes are not active. So you find that they're not toxic. So the toxicity we observe here really comes from SN38 rather than the nanotubes. You can see you can go to very high concentration in nanotube before you start seeing some toxicity. So that got us really excited. So if we look into now again our spheroid model in 3D cells, so we're comparing here a control. So you see the spheroid at day 1 has grown after day 5. Not only it's preventing its growth, but it's actually shrinking the spheroid. So that means that SN38 is really efficient at just not preventing the growth of the cell, but even killing the cells. And as you come to irinotecan, and you find that irinotecan is not as efficient. It's preventing growth, but it's not reducing the size. And this is our compound. And as you can see, not only we're preventing the growth, but in this case as well, we're just reducing the size of the spheroid. So really our delivery system is not hindering SN38. In fact, it makes it as efficient as if it was not delivered. But the point, of course, is to use delivery. So what we want is to use our system to increase its biodistribution and its circulation time in the system. And these are the graphs, and I'm going to go a bit quick on this. I just wanted to focus on this graph here. So those two graphs are the same information. The one is giving you the concentration of drug in solution in mole, and the other one in microgram per ml. Sorry, micromolar, in this case in microgram per ml. And basically you get the same information. What you find is that irinotecan is cleared. So this is the clinical use drug. It's cleared very quickly. Within 6 hours, it comes out of the animal. What our system is doing its job, we have very long circulation time and very long biodistribution. So it is working. And I'll finish off by showing you the example of on an animal that is carrying a tumor. So now what we have here is a series of animals which are all growing a tumor. And we're looking into the effect of a control. So this is just PBS. And as you can see, the tumor is growing. So what you're looking at here is the size, the volume of the tumor. So with time, the tumor is growing, as you would expect from a cancerous tumor. If we treat it with irinotecan, we delay the growth, so we slow it down, and that's what irinotecan is supposed to be doing. But if we use our drug delivery system, as you can see, we got much more dramatic effect on the reduction of the growth of the tumor. So much more effective. None of the systems are toxic to the mouse, so we look at the body weight of the mouse to make sure that the mouth is kept healthy. And I tend to look, as a polymer chemist, I tend to like to use pictures when we talk about biological effects. So these are pictures of the actual tumors taken out of the animal, and you're comparing the control to our nanotubes to irinotecan. And if you look into a few examples, you'll see that in almost all cases, the tumor is going to be shrinking much more with the nanotube than it is with the control, of course, but more importantly, with the irinotecan. So the system is working very well. I think in interest of time, I'm just going to pass on this. I wanted to show you some application in terms of the peptide itself as the drug, but I think I'm going to conclude here to have some time for questions maybe. So I tried to acknowledge the people who did the work, but here is a picture of the group, and you see Sophie here, whose work I've talked about quite a lot here. At this point in time in the picture, Julia already left the group. Robert Darman is my collaborator at WMS Medical School in Warwick, with whom we do a lot of the animal work, and Santosh is an assistant professor in the group as well, focusing on animal work. And I'd like to thank all the people who are funding this work, and finally, I'd like to thank you for your time and for your attention.